So I considerably revised it. So perhaps I should give it a subtitle. I don't think this is the end of physics. And the reason I say that is that Lev told me, at least in private, and perhaps he may assert this or has already asserted this during this conference, that the many worlds interpretation is so good and so satisfactory that actually there is little left in physics. Am I misquoting? Oh, so that's it, okay? So with this, I am taking an exception. And here it goes. I've never been a fan of the many worlds interpretation. But some 30 years ago, actually exactly 30 years ago, I've been fortunate to meet a very brilliant physicist. At that time, he was young. I was young too. And together, we collaborated on something which is known today, after 30 years, as the Elitzur-Weidmann bomb testing experiment. We quarreled a lot since that time about all kinds of issues, but it is through this, and this is why I was so lucky. Lev and I collaborated on this. Was it because it was a good idea? I think so. Was it because he liked me? I'm not sure. But he thought, and he still thinks, that the bomb testing experiment is one of the best, is a very good expression or a very good test to the validity of the many worlds interpretation. So this was very fortunate. And then during all those years in which we argued and quarreled and so on, I had to pay attention to this interpretation, sometimes be struck by its beauty, although I was never convinced. And here is an opportunity to make a dialogue with him. So you probably know, here is the story. You place a bomb, super sensitive bomb. This is the version which I like most. It is not that the bomb is blocking the photon, but it is enough that one of the mirrors gets a kick to detonate the bomb, and it's enough that the mirror that can move does not move to make the photon emerge to the left side detector, and then we are sure that the bomb is good. And there are many questions, how could this be? I would call them philosophically, I would say that there are two main approaches to explain this in philosophy. One is no ontology, and the other is excess ontology. So in no ontology, we will take Copenhagen and other views like this, which say that physics actually doesn't tell you what is reality, but physics tells you what you can say about reality. So it is just knowledge. The bomb did not explode. You know that the bomb did not explode. It's an epistemic fact. That's enough to explain the strange fact that although the photon could not pass through this left path, it left a trace, a causal trace in the photon emerging to the wrong detector. On the excess ontology would be Bohmian mechanics and, of course, the many worlds. So I would say the following, that according to Lev, just at the moment that the bomb did not explode, there are already two Levs, that is, two worlds in which there are two Levs. And if the bomb does not destroy the laboratory and you can proceed with this, then by the time that it emerges and the left side detector clicks, then you have now four Levs, four universes, and so on and so on. And with this, I was never convinced. Again, in alternative to these philosophies, some 10 years ago, Eliyahu Cohen and myself proposed a physical solution. I believe that this is a solution to what is actually happening in the bomb testing experiment. It does not resolve the mystery, as I will show, but it takes us to a place where you don't have to lean on any philosophy. This is what we call the quantum oblivion. I will describe it very, very shortly because it's a very clear paper which you can find. We followed Hardy and proposed the case and a thought experiment in which two superposed particles measure one another, the position of one another. So they make interaction-free measurement on one another in the following way. In order to make it interesting, so I have here a particle and an antiparticle, electron and positron, and they are, just like in the Mach-Zehnder interferometers, they are split. But they are split in such a way that the left part of the electron crosses the two parts of the positron. And don't mind the technicalities, we arrange it such that if they ever meet, then there will be an annihilation. Okay, so here are the two wave functions. There could be an annihilation in this case. There could be another annihilation in the second meeting, but if and then of course they will emit they will emit photons. That will happen in half of the cases. But what happens in the other half of the cases? Well, something very interesting. If the two detectors do not click, they did not register a photon, so there was no annihilation, you have something interesting. The two annihilations did not take place. What do you have? You see that the electron has collapsed, that it has been disturbed, it is only on the right side. While the positron remains oblivious of what happened. It has returned to its original superposition. I'm talking physics here. If you try to time reverse them, then the positron will be completely time reversed. You see it will go back to its source, whereas the electrons sometimes go through the beam splitter to another place. So momentum has changed in one particle, not changed in the other particle, in apparent contradiction to Newton's third law. Here you have an interaction, and one of them is changed, the momentum is changed, and in the other it does not. What is happening here? We can explain that through the uncertainty principle. I urge you to read the paper. The interesting thing is that you see here two detectors which did not register a photon. This is a step further than the IFM. It is not that the photon did not go on this path. The photon was never emitted. The detectors never registered the photon. And still, the electron has changed its momentum. It has collapsed, while the positron never changes. We can show that there was a time in which they were entangled, and then there was an unentanglement, not disentanglement, unentanglement in the sense that something is being reversed. So this, I think, shows something very interesting about quantum mechanics. Quantum mechanics is a branch of physics dealing with the smallest amounts of energy and matter, where events can happen and then unoccur. Nature can sometimes reverse its course and annul and undo some interactions. And this explains how come that the positron is oblivious of what happens, although if we catch it in the middle, we can see that it has been entangled briefly with the electron. And then we argued that what happens in the IFM is something very similar, and this is just physics. You can show that in order for the sensor of the bomb, or the mirror in this case, to have a clear momentum that is zero before and after, it must be smeared. It must have an uncertain position. So something similar happens in that the photon, half of the photon, meets that sensor, just like the positron, in many places, and then they perform kind of mutual interaction, free measurement on one another, and then the sensor tells the photon, look, why don't we say that you have never been here, you have been always in the other place, and I return oblivious, and this is what happens in the bomb. Does it solve the mystery? I think that this is a major advance. It has to do with Aharonov bomb effect and in many other things. You could see that the title is somewhat arrogant, a master key for many quantum riddles. I urge you to read the paper. Still, I don't think that we have resolved the mystery. You have here two interactions which could occur, two remote detectors which could register photons. They did not register any photon, and still one particle, that is the electron, is changing. How is it happening? I said that I was very fortunate to meet Lev some 30 years ago. Lev and I were very fortunate to have this master. And it is once again a testimony to Lev's fertility or his kind of schizophrenia, where he can be a very loyal, many worlds person, and at the same time do all these brilliant works with Yakir Aharonov along the two-state vector formalism. And without feeling any contradiction, for him, they go in harmony. I would like now to show this, to treat the interaction-free measurement in terms of Aharonov's two-state vector formalism. And I would say the following, and here is a brief introduction. What is so annoying about quantum mechanics? Simple. You have a photon going through a beam splitter, and then you have two detectors. You don't know which of them will click. And it is not that it goes one way and not the other. We know that if we make a Mach-Zehnder interferometer, then we can prove that it was in both cases. This is where I am struck by the beauty of the many worlds, because Lev actually says, you see, here is the beginning of universe being split, and we avoid it and we just return it. But here is a kind of proof, or if you want evidence that the many worlds interpretation is correct. But here is a problem. There's only one of them, and I don't know which of them will click. How should I call the other history? There is one future which materializes, I don't know what. How should I call the other future? We had a president, the earlier president of the United States, who enriched our language with something very beautiful, fake. So may I call it fake future? There is a real future and fake future. But the genius of Trump is nothing compared to the genius of Aharonov, because Aharonov says, now when you run it backwards, this fake future is a problem in quantum mechanics because it's not there. It doesn't happen, but the interaction-free measurement tells you that even such a fake future can have causal effects. But now, along comes Aharonov and say, run it backwards. And if you run it backwards, you get also a fake past. I mean, or if you really do want to run it, it doesn't always go to the source. Sometimes it can go to the sewage or to the refrigerator from which it never came. So you have a fake future, and now the TSVF brings further problem in the form of fake past. Why is it good? Why do we need this additional annoyance? Well, here it goes that in a history where there is fake future and fake past, if they overlap, if you take the right initial pre-selection and post-selection, a real effect can happen in the overlap. And this is what I want to show. Here you have, as you can see, one fake future. The bomb did not explode. In terms of the many worlds, there is another universe in which it has exploded. Now, what do you do with the pieces and so on? But it's a fake future. When you run it backwards, there is also a fake past. That is, that the photon came from the bomb, which is not true. But then, as you can see, here is a case in which the combination of the two tells you that the photon went only on one side, but in some strange way, it has been affected by the presence of the bomb or by the sensor of the bomb being in this state. So here's one example, and I would like to take another one. You probably know about the 3 boxes paradox by Aharonov. Now you split a particle not to 2, but to 3 in a somewhat different way, and you pick a certain post-selection. Then you can say something very strange, that the particle has, with certainty, existed, resided in one box. At the same time, it has certainly resided in the other box, and it has been in the 3rd box in a kind of a negative presence. It is not that it is not there, but it is there in a kind of negative way. What do you do with this? It's simple matter of the algebra, which gives you this minus sign for the presence. I usually, Yakir is not here, so he won't object. I usually compare this to what Dirac did many decades ago when he encountered this strange plus in the equation of the electron, and he dared to, had the guts to say that that means that we can have a positive electron. And it turned out to be correct. Yakir said, let's assign this minus sign. We cannot assign it to the charge. Let's assign it to the mass. You have a kind of negative particle, very briefly, for a very brief time, you have it there, and can we prove it?